Assalamualaikum and good day everyone. In this video, we are going to talk about system of linear equations and later on Cramer rules. Now regarding to system of linear equations, let us start with something familiar. A single linear equation. For example, y equal to 2x plus 3 is just a straight line. What happens if we have another line? Say y equal to negative x plus 6. So we have the first and the second equation. Now to solve it, we can try to make the third equation in terms of x. Let us use the second equation here, right, and make it in terms of x. So we have x equal to negative y plus 6. So this will be the third equation. Now we have the equation in terms of x. Let's substitute it into the first equation. So 3 into 1. So we're gonna have y equal to 2 negative y plus 6 plus 3, right? And what do we get here? Y equal to negative 2y plus 12 plus 3. So y equal to negative 2y plus 15. So 3y equal to 15. Y equal to 5. Alright, so this is the value of y. And let's solve for x. Let us sub y into the equation. So sub y equal to 5, right? Sub y equal to 5 into 3. Right, so x is equal to negative 5 plus 6. So this will be this plus 1. So y 5x 1. So yes, we have solved this in terms of the x and y, but what does this x and y values really mean? Let's try to look at it graphically. This is the graph of the first equations. Okay, right now you are seeing it. Now let us try to add the second equation, right, and see what happened. So this is the second equation. So now we are trying to understand, we are trying to appreciate what does actually the value of x and y that we have solved meant. So basically what is actually here is the intersection, right? We have y 5x1. It is actually the intersection of the equation. Why do I actually need to tell you this? Because in system of linear equation, you will need to actually be clear with this understanding before we proceed in discussing the type of solution in system of linear equation. Okay, now that we have clear on this, let's go back to our books and proceed with other information on linear equation. So basically what you see just now, the x and y that we got right from solving this equation is actually an intersection point, right? And this intersection point that gives the value of x and y that satisfy both equations at the same time. They intersect, and that is exactly what a system of linear equation means. Now, reflecting to the matrix structure, we can say that this kind of matrix, or this kind, right, we can say that it is a 2 by 2 system, right? It is actually 2 by 2, right? So for this one, it is actually 2 by 3, and this one 3 by 2. It is if reflected in terms of matrix structure, meaning when we convert it into metric, that is actually the metric size that we will get for each of these particular metrics. But not all systems behave the same. When you plot the equations, three things can happen. Remember that when we plot this equation, what happened is what happened is that we see that the lines meet once, only one intersection point. So we can say that it has one unique solution. We have one value of x and one value of y. But there are also a kind of system of equation where the line overlaps completely, meaning that there will be two lines, let's say, overlap each other. So we have one line, another line is actually also on the same area, on the same line. So when they overlap each other, what does it mean by that? It means that a system has an infinite number of solutions, right? Because the intersection points actually everywhere along the point, so it can be any point. So you have infinitely many intersection points between the two lines. All right, and the other situation is that the lines never met. So basically, we have a graph that is actually has line that is not met, maybe parallel, but they're not met, so they don't have intersection point. So this kind of system is said as a system with no solution. So you cannot find the value of x and y for this case. Now, what we did until now is that I'm showing you a type of system of equation that have one solution, many solutions, and with no solution through a graph. Right, by looking at whether the graph is actually intersects one times, intersects many times, and maybe not intersect at all. But how can we find those intersection points without graphing everything? So for a small system, maybe 2 by 2 and 3 by 3, we can use a rule called Cramer's rule. It is a quick and elegant method based on determinants. Cramer's rule gives us a formula to find each variable directly from determinants. Let's start with assuming that we have this 2 by 2 system of equation. The first thing to do is to find the determinant of it, right, by doing it like this. Of course, we can start by tabulating it in a metric form. So we can have it like this. So we can have A11, A12, A21, A22, and then the x and y, we have this is actually for x1 and x2, and then equal to b1 and b2. Or to make it simple, we can also write it in a form kind of augmented metric forms, which is just between the coefficient matrix and constant metric. Alright, so first, of course, before we do anything, we will look for the determinant. So we are taking this, the whole thing, right, for this 2 by 2 case, find its determinant and make sure that it is not equal to 0, because if it is equal to 0, it is actually cannot be calculated. Right, when the denominator is 0, it cannot be calculated. So assuming that the d is not equal to 0, the next thing to do is to substitute this metric according to the x. So when looking for x1, we substitute the constant metric into the x area of its coefficient. Hence, this is what you get over d. Then for x2, right, we will substitute the coefficient metric of x2 with the constant and over determinant. So basically, for the numerator here, we also, the way to calculate it is exactly like this, which is finding the determinant. So and then after the calculation, just divide with d, and you directly get what is the value of x1, what is the value of x2. That is the Cramer's rule for 2 by 2 system. Now, the same idea can be applied for Cramer rules for 3 by 3 system, where when you have an equation like this, you have 3 equations with 3 variables. So if you try to write it in a form of matrix, in augmented matrix, alright, this is actually how it should look like, and be 3. So in the case of 3 by 3 system, the same idea applied. First, we look for the determinant. So when it is 3 by 3, of course, we can use the idea of cofactor expansion, where you choose only one from column or row, and then conduct cofactor expansion to get the determinant, and after that, make sure that it is not equal to 0 for us to be able to look for later on x1, x2, and x3. So after you have looked for determinant, right, this is actually the determinant using the whole coefficient metric. Next thing to do is, like what we did in 2 by 2, to find x1, we are going to replace the whole coefficient for x1 with the constant metric, and then calculate the determinant for this one, divide, and you will get x1. And for x2, substitute the coefficient for x2, the whole coefficient for x2 with the constant metric, then calculate. And for x3, as you can guess, substitute the whole coefficient metric of x3 with a constant metric and calculate. Let us try to see some example on how they actually calculate it. Look at example 2.23. So this is the example of 2 by 2 system, right? So this is how actually they change it in a form of metric, and then you'll see that the first thing to do is finding the determinant of this one, and they get it -14. So it is not equal to 0, so we can proceed. So the next thing to do is to look for x1. So for x1, you will need to substitute this x1 coefficient with the constant coefficient. So this is what it become, and then conduct the calculation for determinant at this point. You get -28 divided with 14, you get x equal to 2, x1 equal to 2. The next one, you are going to substitute the coefficient for x2 with the constant metric, and then this is what you get. Calculate its determinant, you get 14, divide, you get -1. So for this case, x1 is 2, x2 is -1. And next, again, for 3 by 3, same idea applied. The difference is just in how you calculate the determinant, because of a 3 by 3, the way to calculate it is a bit long. You can try to use cofactor expansion, and you should get this kind of numbers and solve for the x. But again, in matrix, make sure your determinant is not equal to 0 in order to solve for anything, literally anything. So if the determinant is equal to 0, usually it is undefined, it is unsolvable, the system is actually have no solution. So that's it for this video. Thank you and Assalamualaikum.